There was a question recently on the Electronics Stack Exchange site, and it was really a pretty simple question. It said, hey, I want to test the voltage of a battery. It's nominally 12 volts, so I want to tell if it's at or above 12 volts, or I want to detect if it's dropped somewhere between 6 and 12 volts, or if it's dropped way down to somewhere between 0.5 and 6 volts. And the answer was, well, just use 3 comparators with 3 different trip points, one at 12 volts, one at 6 volts, and one at 0.5 volts. And that certainly works, nothing wrong with that, but it got me thinking about comparator circuits and specifically window comparators. And this reminded me of an interesting circuit that I'd first seen in an old Burr Brown Applications of Operational Amplifiers book. And it's this circuit right here. Now this is a window comparator circuit, although unlike most window comparator circuits, it only uses one op-amp. Most window comparators use at least 2. It also is slightly different from a typical window comparator in that it not only tells us whether our input voltage is inside or outside of our specified voltage window, but it also tells us if the input voltage is above or below our specified input voltage. Now, most window comparators will only tell you if you're inside or outside of your voltage window. This one actually tells you if you're above, below, or inside the voltage window. And it does it with just one op-amp. So let's take a look at this circuit and break it down and see if we can figure out how it works. So let's start with this circuit. We have an inverting op-amp with feedback connected through diode D1. We also have 2 voltage sources connected to the inverting input of the op-amp. We have a plus 5 volt source, and we'll assume that's just a fixed 5 volt source here. And we have our input voltage, which would be the input from the battery, for example, that we wanted to trigger on. And for simplicity, we'll assume that R1 and R2 are the same value. So let's assume that Vin is 0 volts. If that's the case, then we can see that we really just have a voltage divider here with R1 and R2 between 5 volts and 0 volts, which means if we ignore the op-amp and the diode, this point would otherwise be 2.5 volts. And we can really simplify both of these voltage sources and these resistors down to a single Thevenin equivalent circuit, where we have a voltage source of 2.5 volts and a resistance that's 1/2 of our original resistor, since they were both equal. Just makes things simple. Now, we can see now we have a 2.5 volt, positive 2.5 volt voltage source connected to our inverting input of the op-amp. So, because this is an inverting configuration, the op-amp will start to drive its output negative. Now, it doesn't have to go negative very far, though, because we have this diode here, D1, and because it's connected through this resistor to a plus 2.5 volt source, it will be forward biased as this goes negative. So what's going to happen is this is going to drive down to about negative 0.65 volts. And at that point, because there's going to be a 0.65 volt drop across the diode, the input here is going to be held at a fixed 0 volts. So the op-amp is happy, both of its inputs are at 0 volts, and it's just going to stay here with an output of negative 0.65 volts. And this is going to hold true for any positive input of Vin, because as Vin goes up, we're just going to drive this point really more and more positive, so our Thevenin equivalent voltage is going to get larger and larger, and that's just going to keep this diode forward biased, and the output of the op-amp will continue to be negative 0.65 volts. And that's really not terribly interesting, but things start to get interesting when Vin starts to become more and more negative. So between 0 and negative 5 volts, nothing interesting really happens because this Thevenin equivalent voltage that's connected to the inverting input of this amplifier is still positive. So as long as it's at 0 volts or above, this diode is going to remain forward biased with the op-amp putting an output of negative 0.65 volts. And therefore the op-amp will still control this input and it'll stay at 0 volts. Now at negative 5 volts, we can see that we have two equal but opposite voltage sources, and again, assuming R1 and R2 are of equal value, the Thevenin equivalent here is just 0 volts connected through a resistor that's half the value of R1 and R2. So there's going to be 0 volts here, and the op-amp output will actually go to 0. But what happens when this voltage drops even slightly below negative 5 volts? Let's say it goes to negative 5.1 volts. Well, once this voltage drops below the absolute value of this voltage, our Thevenin equivalent suddenly becomes a negative voltage source connected to the inverting input of the op-amp. Now, because the op-amp is in an inverting configuration, he's going to start outputting a positive voltage here. But because this point is connected to a negative voltage source, a positive output from the op-amp is going to start reverse biasing this diode. And as soon as that happens, we don't conduct anymore. This diode's shut off, and the op-amp has now cut itself off from the feedback loop. So the op-amp suddenly finds itself in an open loop configuration. It still sees a negative voltage here on its inverting input, and it's just going to keep driving its output until it hits the positive voltage rail. So for a rail-to-rail op-amp with a positive voltage rail of plus 5 volts, you would see 5 volt output here on the op-amp. So what we have here is an inverting comparator where the trip voltage is defined by the Thevenin equivalent of these two voltage sources and these two resistors. Specifically, when the Thevenin equivalent voltage goes negative, the output will go high. And otherwise, the output will sit at negative 0.65 volts. For digital logic, that's close enough to 0 to be considered a low voltage threshold. Now we can more formally define the trip point of this comparator circuit by saying that when the total sum of voltages connected to the op-amp's inverting input crosses the 0 volt threshold, that's when the op-amp's output will go high. In other words, when Vin multiplied by the voltage divider of R2 over R1 plus R2 is added to V plus, which we were just assuming was 5 volts in our previous examples, times the voltage divider of R1 over R2 plus R1 is equal to 0, that's where our trip point lies. And now that we have an equation to describe our trip point threshold, we can rearrange this to solve for Vin by subtracting this part from both sides, multiplying both sides by R1 plus R2 to get rid of the denominators, and then dividing both sides by R2. And now, with this equation, we can predict at what voltage of Vin the op-amp's output will go high, given our R1 and R2 resistor values and the V plus voltage. Now, one thing you'll notice is that there's a negative sign here, which means that the trip point is always going to be a negative voltage, which we really already knew because any positive voltage is just going to keep the diode D1 forward biased, and the op-amp's output will just sit at 0.65 volts. It also means that if R1 and R2 are equal value resistors, then the trip point is simply the negative of the V plus voltage. To demonstrate this, I have that exact same circuit built up on the breadboard with R1 and R2 equal value 2.2 kilo ohm resistors and V plus set to 5 volts. Now I'm feeding V in with a sine wave that goes from negative 10 volts to positive 10 volts. And you can see that as soon as the input voltage drops below the negative 5 volt mark, the output of the op-amp goes high. And it stays high until that voltage comes back up above negative 5 volts. And for all other voltages between negative 5 volts and positive 10 volts here, the output is just below 0 volts from the op-amp. Now let's consider what changes in the circuit when we add diode D2. Everything else is the same, we just have this one additional diode. Now the first thing that you'll notice is that the equation for our Vin trip point has changed slightly. And that's because we have to account for this additional diode voltage drop of D2. So we have to subtract the forward voltage of the diode from our V plus voltage source. But otherwise, the equation remains the same. Another thing to note is that the output of the op amp is typically going to be 0 volts, right? Because he's going to be trying to hold this point at 0 volts. So if he outputs 0 volts, provided both of these diodes are forward biased, this point will then be at positive 0.6 volts, and then there'll be another 0.6 volt drop across this diode, putting the inverting input at 0 volts. So for negative input voltages, the circuit operates exactly the same, aside, of course, from the extra diode drop here. And the output of the op amp is going to be 0 volts until Vin goes down below our trip point, at which point D1 is again reverse biased and the output of the op amp goes high. However, D2's purpose comes into play when Vin gets to be 0 volts or above. Now, when Vin is negative, the op amp is going to be holding this point at 0 volts, and so we're going to have current flowing out this direction. Once Vin gets up to 0 volts, of course we'll have 0 volts across R1, and so there'll be no current going through R1 at all. But once Vin becomes even slightly positive, this point is a positive voltage, this point is 0 volts, and so we're going to have some current flowing this direction. Now that current can't go up through diode D2 because D2 only allows current to flow in this direction, so it's going to have to go into the high input impedance of the op amp, and a very small current going into a large resistance can start to develop a very noticeable positive voltage here. And this is an inverting op amp configuration, so once it sees a positive voltage here, it's going to start driving its output negative. However, as it does that, it's going to drag this point down negative as well. So if this were to go down to, say, 0.6 volts, or excuse me, negative 0.6 volts, this point would be 0 volts because we have the diode drop across D1. And if it went down to, say, 1.2 volts, this point would be negative 1.2 volts. This point would be negative 0.6 volts, and so on. So what we have is a positive voltage here and an increasingly negative voltage here, which means D2 becomes reverse biased, and the op amp has once again cut itself off from the feedback loop. So with D2 reverse biased, the op amp has lost control of the feedback, and it sees a positive voltage here, and it's just going to slam its output into the negative rail. Now we can easily visualize this by replacing the two diodes with two LEDs. And I have the red LED here in the place of D1 and the yellow LED in the place of D2. And I'll kill the lights here so we can see those a bit better on the camera. So I'm currently inputting into my Vin 0 volts. And you can see that D1 is on and conducting and D2 is off. And as I make that input voltage more and more negative, you can see D2 starts to come on and D1 starts to turn off as we pass our voltage trip point. Likewise, if I make the voltage more and more positive, we can see that D2 starts to turn off and D1 turns back on again. And if we take a look at this on the scope, we can very clearly see what's going on. Again, I'm feeding a 20 volt peak-to-peak signal, plus 10 and minus 10 sine wave, into the Vin of the circuit. Again, my V plus voltage is 5 volts, and both of my resistors are of equal value. So once we count that D2 voltage drop, our negative trip voltage is going to be just a little above 5 volts at 4.4 volts. And we can see that as we go negative, once we hit that 4.4 volt mark, the output of the op amp goes high, just as it did before, and it'll stay high until we come back up above that 4.4 volt mark here. And again, just as before, in between the 4.4 volt mark, our negative trip point, and 0 volts, the output of the op amp is 0, or quite close to it. However, once we go up above 0 volts, D2 becomes reverse biased, and the output of the op amp drives to the negative voltage rail. So what we've done is we've built a very simple window comparator, where below our negative trip point, the output goes high. Above 0 volts, the output goes low, and in between, the output is 0. So we can tell when we're inside this voltage window of 0 to negative 4.4 volts, or if we're below negative 4.4 volts, or if we're above 0 volts. So we can construct a little truth table here for this circuit. For any input voltages above 0 volts, the output of the op-amp is going to drive to its negative rail because the loop is open since D2 is reverse biased and off. Between 0 volts and our negative trip voltage, the output is going to be 0 volts because both D1 and D2 are forward biased and the loop is closed. For input voltages below our trip voltage, the output of the op-amp is going to drive to its positive rail because the loop is once again open since D1 is reverse biased and turned off. Now you'll notice here that our high voltage in our voltage window here is always 0 volts, and it's not variable. The other thing you'll notice is, of course, our trip voltage has to be negative. So if you need a window comparator where the window is between 0 volts and some negative voltage, this circuit would certainly work just fine. But what if you wanted your window to be between 0 volts and a positive voltage? Well, we can do that just fine. We just need to reverse our voltage polarities here so that this voltage is now negative, and that makes our trip voltage positive. And of course, we also have to flip the orientation of our diodes. So with our polarities reversed, this circuit works exactly the same as the previous circuit, just in reverse. So now we have a different truth table where below 0 volts, the output of the op-amp is driven to its positive voltage rail because D2 is reverse biased and off. Between 0 and our positive trip voltage, the output of the op-amp is 0 volts because both of these diodes will be forward biased and the loop will be closed. And above our positive trip voltage, the output of the op-amp drives negative because the loop is again open since D1 is reverse biased. Now what's interesting is that these two truth tables are mutually exclusive, so we can combine this all into one circuit built around one op-amp. So above 0 volts, D2 is off, so this feedback loop is open. However, above 0 volts, this feedback loop takes over because it is closed and it controls feedback. Likewise, below 0 volts, this feedback loop is open because D4 is reverse biased and off, and below 0 volts, this feedback loop takes over and closes the loop. So you can combine these two together and you can set a high trip voltage and a low trip voltage. And you can control these individually by controlling the V minus and V plus voltages we have here, as well as the ratio of R1 to R3 and R1 to R2, as you can see here. Now, your high voltage is still going to be positive and your low voltage is still going to be negative because V minus is going to be a negative voltage here, and of course V plus is a positive voltage. But you have a window comparator where you can individually set the high voltage and low voltage as long as your high and low voltages that you're interested in are positive and negative respectively. For example, let's make it easy. I'll set all of my resistors to the same value. So both of these ratios are just going to be 1. And I'll set my V plus to plus 5 volts and my V minus to minus 5 volts. Well, minus 5 volts plus 0.6 volts, accounting for the diode drop here, is going to be negative 4.4 volts. Negative 4.4 volts is positive 4.4 volts. So my high trip voltage is going to be plus 4.4 volts. Likewise, with my low trip voltage, I have a positive 5 volts minus 0.6 volts. That's going to be positive 4.4 volts. And of course, we have a negative sign here, so my low trip voltage is going to be negative 4.4 volts. So above my high trip voltage of plus 4.4 volts, the output is going to be driven to the negative voltage rail. And below my low trip voltage of negative 4.4 volts, the output is going to be driven to the positive voltage rail. And in between, the output is going to be driven to 0 volts by one of these two feedback loops, depending on if my voltage is between 0 volts and my positive trip voltage, or 0 volts and my negative trip voltage. And we can see exactly that on the scope. As my input goes down below negative 4.4 volts, the output from the op-amp goes high. Once I come up above positive 4.4 volts, the output goes low. And in between, the output is 0. But what if we want our load trip voltage to be a positive voltage? For example, what if we want our window to be between plus 6 and plus 12 volts? Well, we can turn this into a summing amplifier, since it is an inverting configuration, and we can add a negative voltage to it. So this negative voltage is going to offset the input. In this case, it's negative 7.5 volts, such that when the input is 6 volts, the total voltage is actually negative 1.5 volts, which gives us a negative low voltage threshold. And when the input is 12 volts, the total input here is going to be positive 4.5 volts. So we do get, by adding this offset voltage, a negative trip voltage and a positive trip voltage for our low and high voltage levels, respectively. And with a plus 7.5 volt and negative 7.5 volt rail, the use of 10 kilo ohm resistors here for R1, a 47 kilo ohm resistor here, and a 15 kilo ohm resistor here, we get pretty darn close to the necessary trip voltages. So these resistor values are selected so that the negative trip voltage is at negative 1.5 volts and the positive trip voltage is at positive 4.5 volts. So I've got this circuit built up on the bench. I'm measuring the output of the op-amp with my multimeter here. You can see it's currently driving its output high, and I'm inputting a voltage of 5.9 volts. So the high output voltage shows that we are below the low threshold voltage of 6 volts, which we certainly are at 5.9 volts here. So I'm going to increment my voltage here to 5.91, 92, 93, 94, 95, 96. Oh, there we dropped down to pretty close there to 0 volts, about half a volt. So the trip voltage here is 5.96 volts. So a little bit off from the ideal 6 volt voltage, but that's pretty much expected. The calculated resistances in the circuit are actually different from the ones I use because I use the nearest standard resistors. So let's see what our high trip voltage is. So we're currently inside the window, so you can see that we're staying, right around 0 volts here as I increase the voltage. And I'll go up here. I'm at 11 volts currently, so we're still inside that window. 12 volts. Output is still pretty low, just right around 0 volts, so it still says we're inside the window. If I go up to 12.1 volts, oh, there we've tripped it. So looks like about 12.1 volts is the high trip voltage here. You can see the output is being driven down to the negative voltage rail. So there you have it. It's a window comparator that detects 3 different voltage ranges with just a single op-amp. There are some disadvantages to this, however. First of all, since it's an inverting configuration, the input impedance is going to be set by this resistor. So in this case, 10 kilo ohms is not terribly high, especially compared to, say, a non-inverting configuration where your input impedance would be the input impedance of the op-amp itself. The other issue is you have some additional errors introduced by the variation in voltage drops across your diodes, which you really can't control very well with discrete components. So you do have some additional error there. So if you need a precision comparator, this configuration is probably not the best. But most comparator circuits don't need to be that precise, and so being able to have a window comparator with one op-amp is certainly quite useful. So I really enjoyed reading through these older electronics books because I find that quite often I encounter clever little circuits that I may not have otherwise found. So hopefully you enjoyed it as well, and if you did, be sure to like and subscribe, And as always, if you have any questions, suggestions, or corrections, leave them in the comments section below. Thanks for watching.